Wow, hello guys. Welcome to my channel. You're welcome to Master Builders Online Academy. I want to use this opportunity to appreciate every one of you who are subscribers to this channel. This channel is actually growing because of you. Thank you very, very much. I want to sincerely appreciate you for making necessary comments at the comment section, sharing our videos, liking our video, and then watching our videos. I want to specifically appreciate those of you who are recommending this channel to other students outside in Nigeria. You guys are really amazing. So guys, in this module, without wasting much of your time, I'll be taking you through a problem again, engineering thermodynamics, right? And then this is a continuation class for those of us that are seeing this content on thermodynamics as the first time. Please, we have other videos made on this course before now, so you can quickly check our playlist. Under the playlist, just check out for engineering thermodynamics, and then you can see previous videos before that. But if you have watched those ones, please, this is a continuation class. So one of the things you must do for us is to ensure that you avoid distractions, pay total attention, so that every principle and every detail I will be explaining why I teach and solve this problem, you would be able to gain it once and then for all. So without further ado, let's just dive into this problem and give it the necessary solution. Okay, now as you can see on the screen, we have a problem, and then the question is this: a single cylinder compression ignition, internal combustion engine. You see the sentence. All of this sentence don't really matter. It's not just a problem at all. Okay, does 9,900 kilowatt of work on the air charged into the cylinder during each compression stroke, while rejecting 700 kilowatts of heat to its surrounding, which is water in the jacket, full stop. During the expansion stroke, all right, the product of combustion does 13,300 kilowatt of work on the piston. Can you see it? On the piston. This is work done on the piston now by the combustion ignition engine. Are you there? So as you can see now, on the engine, work done on the piston. Now the question is, determine the change in energy of the system, question number one, and also the quantity of heat added. Remember that at the expansion stroke, heat is always added. Thermodynamics questions always appear like chemistry, whereby the questions are not always straightforward, not until you have an in-depth understanding about the question, right? So determine the internal change of the system and the quantity of heat added to the system as the contribution of the compression process. So guys, all of these are just English that you don't need to be scared of. All you just need to do now is extract your parameters. What are given? Forget about the sentence. Work is given, heat is given, another work is given for another process entirely. It's as simple as this. Now, one of the things you need to understand is that compression and expansion, they are equal and opposite, right? Opposite. So in compression, heat is rejected. Then in expansion, heat is added. Are you there? It's just like that. So when heat is removed and heat is added, that means something is happening in that place. But let's check out and see with our solution what we are going to have. So the first thing that we're going to do now is that we have to state the given parameters as usual, because this is a word problem. And then to solve this, we just have to do this. Okay, so let's get into the business. So we have given. Now the first thing that we're given is work done from process 1 to 2, and this work done is 9,900 kilowatt. All right, that's the work done from process 1 to process 2, process 1 to process 2. And then this work done was done on the system, not by the system. I want you to read it very carefully. A cylinder compression ignition internal combustion engine does 900 kilowatt of work on the air charged into the cylinder. You see now, it's coming through the air, entering the system. Are you there? During the expansion stroke. So it shows that it was not the system that does the work, but the work was charged into the cylindrical compression system. Are you there? or combustion engine. So if this is clear, it shows that this work as we have it is negative. Again, the heat in this process while rejecting, now we have Q between 1 and 2 is equal to, why I'm using subscript 1 to subscript 2 is because of the process. There are two processes involved here, okay? And then remember that heat rejected again is negative, so we have this as 700 kilowatt. All right, so this is heat rejected. Can you see that? So heat rejected. Then we are now asked to find change in internal energy between this point, change in internal energy, which is the same thing as what? U2 minus U1. I hope you can see this. It's as simple as this, my guys. All we just need to do now is that for this first process, you don't need to waste your time. For this first process, what do we do? This is the first process, okay? This is for the first process. All we just need to do now is to recall the thermodynamic equation. First law, recall that the first law for thermodynamic equation is given as what? Q minus W is equal to change in internal energy. So because we have process 1, process 2 now, then we can have this as Q1 to 2 minus W1 to 2 is equal to change in internal energy. And as we can see from this point, all we just need to do, guys, here to solve this problem is to put in the values. So our change in internal energy becomes Q1 to 2 minus Q1 to this. All right. So what is our Q1 to 2? Is minus 700. So put in minus 700, then minus our work done, as you can see here on this process 1 to 2 is 9,900. So we'll put in the value here, 9,900. All we just need to do now is to simplify it. So this becomes minus 700 minus, sorry, we have negative here. So minus multiplied by minus will give us plus 900. Are we there? So minus 700, as you can see now, minus 700 plus 9,900 would have given us 9,200 kilowatt. This is the work. This is what we have as the internal energy. It's as simple as this. So we have been able to obtain the first value, which is what? Change in internal energy. So we can simply say now, therefore, change in internal energy, this guy, we have a change in internal energy, which is something as U2 minus U1 is equal to 9,200 kilowatt. All right, so guys, this is all about the first process. As you can see, just listed the parameters, and then we are good to go. Now, from the second process, now let's state it. Now, process 2. This is second process. Now, for this second process, you see, now let's read the question very well so that you see it. Now, full stop right at this point. Now, you answer during the expansion stroke. This is now the reverse during the expansion stroke. Now, this is responding back. So it is now from process 2 back to process 1. The product of the combustion does 30,300 kilowatt of work on the piston. You see it now. So it is now the cylindrical combustion engine that now does this work on the piston. So it shows that this 30,300 is the work done by the system. So because this is work done by the system, we are going to have this work as positive 2, positive value. Are you there? So now this is now from, so in this case, we now have Q from 2 to 1 is unknown. And then W from 2 to 1 is the one that is given as 30,300 kilowatt. So because this work is done by the cylindrical compression engine, this work done is positive. Now, when we come back to the internal energy, because this is reverse process, like I mentioned before, so we are now having this as change in this is now U1 minus U2. And I gave you this equation today that when the equation is now a reverse one, that this internal energy becomes negative. Are you getting it? This internal energy becomes negative. It becomes negative. Why? Because of the fact that this is a reverse process. Just look at something here. This is the process. Okay, this is process 1, then this is point 2. So the journey began from here and moved to this. So this we have as U1, and then we have U2. We call this change in U. Please just look at what I'm doing here. So change in U is always final minus initial. So if it moves from 1 to 2, it becomes U2 minus U1. And now if it moves from U2 to U1, like this case now, when I have it like this, okay, then it becomes change in U is equal to U1 minus U2. So this is now negative value. So it shows that our change in internal energy now will be negative of the value we had before, which is 9,200 kilowatt. Hope you can see this. So the reason why this value is turning to negative is because it's a reverse process. So if forward reaction is positive, then the backward reaction is negative using the equilibrium approach. You understand the condition now? So if this condition is clear very, very well, all we just need to do, guys, is to now recall our equation again. Remember, in this second process, all we are looking at is what? The heat added, right? Now heat added. So we just recall again the first law of thermodynamics, that this minus this is giving us what? Change in internal energy. Can you see this? And then we now call this, okay, from process 2 to 1 minus process 2 back to 1 is equal to change in internal energy. All I just need to do now is that since I want to obtain the value of Q, we can make use the Sawyer formula. 1 to 2 is equal to, as this guy crosses, it becomes positive. 2 to 1, then plus change in internal energy. This is what we have now as the equation to obtain the value of heat. Are you there? So we already know that the value of the work done during process 2 back to 1 is 30,300. So what we just need to do now is to put in the value there. 13,300. Then plus the internal work done become 9,200. So by the time we remove the bracket, this is 13,300 plus minus give us minus 9,200. And then by the time we remove this guy from this, we have 4,100 kilowatts. Therefore, the heat added. Remember, why is this heat added? As you can see now, the result we have is positive. So it becomes heat added. But assuming what we obtain here when we solve is negative, that means it would have been heat rejected. Hope you understand it. You get the condition, right? So because the value we have is positive, so it's actually heat added, heat accepted, or heat absorbed. Are you there? And then heat added to the system, you call it. And the system in this case now is the cylinder combustion engine, right? X 4,100 kilowatts. So this is the answer to this very question. So guys, you find out that these things are always very, very easy to solve, as you can see. Very, very easy. So the best way to understand all of these things or to solve problems on thermodynamics very, very well is ability to understand, being able to interpret the question very well, break it down into its least level, and then you'll be able to solve this effectively. I hope you've gained value from this video. Don't forget to leave a comment behind at the comment section. Like this video, share this video, and then make sure you subscribe to this channel if you have not done so. This is the only way you can encourage us and then to keep us doing more of amazing content like this. So guys, without further ado, let me dive you into another question that will also blow up your mind again. Let's dive into that. All right guys, so welcome to my channel again. This is another question before us. Without wasting much of our time, let's quickly examine this question and then provide the necessary solution. Remember, we are problem solver, right? Even you yourself, you are a problem solver. So let's quickly solve this problem together. It's not actually hard at all. It's just a simple question. But the question can be very short, and then the solving is long, and the question can actually be very long with long expressions, sentence, and then all of that, and then the solving process is just very short. But without actually wasting much of our time now, look at what we are going to do here shortly. So the question we have is: a mixture of gas expands from 0.03 meter cube to 0.06 meter cube at a constant pressure of 1 megapascal, absorbs 84 kilojoule of heat during the process. Full stop. The change in internal energy is, can you see it? The change in internal energy is, so this is the question now that we're asked to look for. This is the question. So this is the question already. This is the question that we are asked to solve. Find change in internal energy. So guys, all we just need to do here is to first of all extract the given parameters as usual. It's just as simple as that. Extract the given parameters, and then you'll be able to get equation that connects the given parameters to help you find the unknown. So we have given. All right, so we are given volume, right? And this volume we are given initial volume from this, which is 0.03 meter cube. Then we are given final volume V2 as 0.06 meter cube. Can you see this? And then we are given heat Q, and that heat is given as what? 84 kilojoule. Can you see it? 84 kilojoule. And then we are asked to find internal energy. But remember, work done, W, is not given. And then change in internal energy is unknown. This is actually what we are asked to look for. But as we can see now, using the equation of first law of thermodynamics will be very, very difficult for us to use here. Why? Because we do not know work done. But here, as we can see again, we were given pressure. Let's look at that. Pressure P. And what's the pressure given? We're given 1 megapascal. Can you see it? So we have 1 megapascal, 1 megapascal. 1 megapascal, and 1 megapascal is equivalent to 1 times, what is mega? 10 raised to the power of 6, and 1 pascal is equivalent to Newton per meter squared. All right, hope you remember this. Now guys, we are already good to go. All we need to do now is to first of all find work done. Of course, the question did not require us to find work done, but if you are to have a question like this in objective, for instance, you might be asked to find work done in the first one, and in the second question you are not asked to find the change in internal energy, because both work done and internal energy, they are not given. Are you seeing it? They are unknown. So that means the parameters given will enable us to find the two. So in another question, you might be asked to find both work done and internal energy. But one of the things is, since we are asked to find internal energy, there is no way we can find internal energy here without first obtaining the work done. It's as simple as this. I hope you can see this. So let's look at this. In order to have this done, all you just need to do is to remember work done. Remember, in one of the videos we worked on before, we said that work done between two processes, 1 to 2, is equal to what? Pressure multiplied by change in volume. You remember this formula, which is said that pressure is equal to V2 minus V1. I hope you are beginning to gain massive values already. So this is it. So these parameters that we just have here, guys, V1, V2, and then the pressure that we are given so that we can find work done. Having obtained work done, now we just remember the first law of thermodynamics, and then we apply the equation. We are good to go with the internal energy. Are we there? So okay, let's move on. So we have work done is equal to 1 multiplied by 10 raised to the power of 6. We are just substituting. We just put in the value of pressure now. Then for the other, we have 0.06 minus 0.03. All right, so when we have this done, what will become our answer? Our answer automatically becomes 1 times 10 to the power of 6 multiplied by 0.03. 3. Remember, if you remove 0.03 from 0.06, you will still have 0.03. And then by the time we add this together, what do we have this to become, guys? This would have given us 3 times 10 raised to the power of 4 Newton meters. Now you understand very well that 1 Newton meter is the same thing as 1 joule. So this is same thing as 3 times 10 raised to the power of 4 joules. Now this is the work done, but you need to check the heat that we're given is in kilojoule. Can you see it? So that means we need to also convert this work to kilojoules. How do we convert this work to kilojoule? We just have to divide this result by 1000, and if we do, our outcome becomes 30 kilojoule. This is the work done for this particular process. Now, having obtained the work done, guys, all we just need to do is to get the internal energy. Now, coming back to the heat, now let's quickly look at this now. Coming back to the heat, we find out that this heat was absorbed by the system, right? Absorbed by the gas. So because it was absorbed, it shows that this heat is positive because it is heat accepted, heat added. The same thing, because this is an expansion process, expansion, that means it is the system that is doing work. So because the system is doing work, our work done, as we will have it again. All right, so in summary now, work done will be equal to plus 30 kilojoule. Why? Because in an expansion process, it is the system that does work. Are you there? So if this is done, then all we just need to do now is to recall our first law of thermodynamics. Are you there, guys? So are you there? All right. Now, stay fixed. Now we recall that Q minus W is equal to change in internal energy, or change in internal energy is equal to Q minus W. We were given Q to be what? 84 kilojoule. And then we just calculated for work done as 30 kilojoule. When we remove 30 from 84, our answer becomes 54 kilojoule. This is the answer to this very question. So you see that it is very, very simple. Therefore, the change in internal energy is 54 kilojoule. So guys, as I promised, I have actually showed you how to solve this kind of problem without actually wasting much of your time. It's very, very simple, very, very simple. It's just understanding that you need. I hope you have gained value so far. So don't forget to subscribe to this channel if you have not done so, and ensure that you turn on the post notification bell for more content like this. Don't forget to give us a thumbs up. Don't forget to like. Don't forget to share, and don't forget to leave a comment at the comment section. So without further ado, guys, let's jump into another question entirely. All right, guys, welcome to my channel again. Here we have another question before us. You're welcome to Master Builders Online Academy. Now let's quickly look at the question that we have before us without wasting much of our time. Okay, now the figure below shows 3 quantitative processes by which a gas may be taken from one equilibrium state 1 to a second equilibrium state 2, from state 1 to state 2, as we can see in the diagram. Now, first of part A is an adiabatic process. Adiabatic process, which is at constant volume. Are you there? Part B is a process of, as you can see from there, part B is a combination of a process of constant volume and a process of constant pressure. And part C consists of a process of constant pressure followed by a process of constant volume, as you can see right on the screen. Okay, if internal energy at state 1 is this, don't forget internal energy at state 1, that means at the initial point internal energy is given as this. determine the internal energy at state 2. That means we are given U1. Now let me change the color of the question so that you can see what we are actually looking at. Okay, let me change this to another color. Can you see it? All right, so now we are asked to determine the internal energy at state 2 and internal energy flowing into the system during the 3 parts. So now we are given that work done at A, which is the adiabatic process, is equal to 99, and then work done at process B is 80 joule, and then work done at process C is 130. So as you can see for this question now, it is very, very clear that the work done for each processes are given, but the heat for each processes are not given, and the internal energy are not given. But one of the things is that because this process involve just 2 points, are we there? We have 2 point 1, as you can see in this diagram, point 1 and then point 2. Let me zoom it out for you. So let me zoom it out for you so you can see here we have point 1 and then we have point 2. So between these 2 points like we have here, we have 2 internal energy, one at 1 and then the other at 2. Can you see it? The other is at 2. So if this is clear enough, now let's move ahead to. So what we just need to do again is to start taking the processes one after the other. Start taking the processes one after the other. So what we are going to take now is part A. Remember, it is in 2 parts. So this is the first part, part A. As you can see here now, this is part A. So, and the part A, which is adiabatic process. So let's take that. So in this case, in order for us to extract the parameters, we are going to be taking it part by part. Hope you understand that. Part A. Now in this part A, what process is it? Part A is adiabatic process. I hope you can see this. Adiabatic process. Adiabatic process. Now, what do we need to do? Let's extract the given parameters. Now, guys, for every adiabatic process, heat Q is always equal to 0. Heat is 0 for every adiabatic process. Heat is always equal to 0. Now, what is the work done on this process? As you can see from the question, we're given that work done at A, which is same thing as WAD, is given as 99 joule. Let me take you up so that you can see it. So this is the work here, as you can see here. You can see it on the screen. WA is equals to WAD equal to 99 joule. So this is the work done for this adiabatic process. Now the internal energy U1, remember it's not changing internal energy, was given as 490 joules for process 1. Now let's move up. And now as you can see from here, we have that part this and this and this of this as we have that. And then as you read further, it said if the internal energy at state 1, at point 1 is 490, not 590, is 490 joules like we have now. Then we are now asked to find the internal energy at point 2. We are finding internal energy at point 2. So we now put again here internal energy U2 is unknown. So now, what is now change in internal energy? Change in internal energy is equal to this guy and is unknown. But don't forget that change in internal energy is always equal to U2 minus U1, because this is the first process, which is from process 1 to 2. So we are removing initial from final, right? So let's assume we have this here now so that we will not be able to go up. This is 1 and then this is 2. So from 1 to 2 becomes 2 minus 1. You get it? Then if it is 2 to 1, that's when you now have 1 minus 2. Okay? So if this is clear, all we just need to do now is to recall the equation of first law of thermodynamics, and that equation is given. Recall that Q minus W is equal to change in internal energy, and then this is Q minus W is equal to U2 minus U1. All we just need to do, guys, is to put in the values here, and then we are good to go. That's all. Good to go. Good to go. So we have Q to be 0 as we have, and then minus the work done is 99 as you can see there, which is WA. Okay, assuming I want to put it this way now, then U2 minus U1. So WA as we have here is given as, so this automatically gives us WA is equal to U2 minus U1. In order to make U2 the square of formula, we just have U2 is equal to U1 minus WA. What is U1? 490 minus what is work done? WA 99. And then if we remove 99 from 419, we'll have this as 391 joules. Remember the units we are given in joules. It's as simple as this. This is just all about the work done for the first process. Remember, there are 3 processes involved, right? 3 processes involved. 3 processes involved, which is part A, part B, and part C, as you can see even in the diagram. So now we are done with part A. The next part now is part B. So now let's take part B. Part B. Now, if you read from the question, in part B, we have constant pressure process. This is what we have. So for constant pressure process, one of the things you must understand that for constant pressure process, work done is already given at this level, right? Work done at B is already given. So we just need to extract the parameters. Work done here is already given. Change in internal energy is also known already. Are you there? Okay. Then, what else again do we have here? And then we are looking for heat. Remember that the internal energy for this process has already been obtained. So what we just need to do now is to extract the given parameters. From here, we have that work done at B, WB, is given as 80 joules. You can check it up here. Is here. That's 18 joules as we're given here. Look at it here. 18 joules, right? And then if we move down, heat at B. Heat at B is unknown. Now let me rule here. Now remember, change in internal energy is the same thing as U2 minus U1. So I can decide to calculate for change in internal energy separate, which is now, if you come up here, what's our U2? U2 is 391, then minus the internal energy at process 1 is 490. And then the internal energy, change in internal energy in this process would have given us minus 99 joules. So this is the change in internal energy on this process. So all we just need to do is to recall the first law of thermodynamic equation. All right, and that equation says that Q minus W is equal to change in internal energy. So I can call this QB minus WB is equal to change in internal energy. Meanwhile, there is no change in internal energy at B. The change in internal energy is the same all through. Is the same all through. Only that if you have reverse reaction, the value becomes opposite of what you already have. Is that clear? Okay, so we just put in the value. Since we are looking for QB, here we have QB is equal to change in this guy plus WB. Anyone can actually come first as long as both are positive. So what do I do? Change in internal energy, if we substitute, this is negative 99. then plus the work done is 80, as you can see from here, right? Now if we solve this further, we have that minus 99 plus 80, and the resulting value here is minus 19 joules. So guys, we have been able to obtain the missing data in part 2, which is part B, at constant pressure process. Now we are left with part C. All right, so the same thing we are going to do now, we're going to take part C. Meanwhile, at part C, we were already given the what? The work done there, which is WC. Now the question is, guys, peradventure you are asked, what type of heat is this? Because this heat is negative, for instance, before we move down, therefore the heat is rejected. So you can now say heat rejected is equal to minus 19. Heat rejected is equal to 19 joules. So once you put in this heat rejected, it shows that this value here is negative. So as long as the heat we obtain, the value we obtain for Q is negative, it means that the heat was rejected in this process. Now if we come to part C, again we move down to part C. Part C. From this part C, what process, if we look at it, what process is this part C? Now come to this diagram. Part C is constant pressure. Again, constant pressure. As you can see now, look at B, horizontal member. Look at C, horizontal member. So this is constant pressure. This is when pressure value remains the same all through. So C is also a constant pressure process. So we still have this as at constant pressure process. So again, what is the heat here? It's not given. Work done here is given. Now let's slide up so that we can see the value for the work done there, which is the last value in the question. We were given that WC, as you can see here, is equal to 130 joules. So we'll move down and then put in the values. 130 joules. And then what is change in internal energy? The change in internal energy is equal to U2 minus U1. And what is U2 minus U1, guys? U2 minus U1 is negative 99 joules. All we need to do again is to recall the equation of the first law of thermodynamics. So recall that Q minus W is equal to change in internal energy. So if I want to suit this to this particular process, I call this C minus WC is equals to change in internal energy. Being that we are making C the sort of formula, we have this as WC plus change in internal energy. All we just need to do, guys, is to put in the values and then we are good to go. If we do that, the value of work done here is giving us 130. You can decide to use bracket. Then plus the value for this guy is 99, negative, right? And then if we clear off the bracket, we have 130 minus 99. And if we remove 99 from 130, we have 31 joules. Don't forget that this is the unit that we're given. So guys, it's as simple as what you can see here. So what does it mean? Since that the heat that we have here is dust, the energy flows into the system from the surrounding. Are you there? From the surrounding. Therefore, heat is accepted. This heat is not rejected. So heat is accepted because it flows into the system. So that heat is giving us 31 joule. So guys, you find out that we have been able to calculate for all the missing data. We are asked to calculate for change in internal energy, and then after obtaining the internal energy at this level, we are asked to find the flow of energy into the system during these three parts. So the first flow is 0 for any adiabatic process there is no heat. But for every other process that we have here at constant pressure, we have heat, and at constant pressure again for part 3, we have it. So this is all about this question. So guys, in order to solve problems here effectively, like I do always tell you guys, is that you must ensure that you are able to understand the question first to know what and what to do. Haven't been able to clear off this question, so guys, make sure you leave a comment below. All right, so we love you guys. See you guys in the next question that will also be so interesting. Let's dive into that particular question. All right, guys, so welcome back again to another session with me. This is the Wise Master Builders Academy. You're welcome. So now we have a question before us, and then this question is not that different from the one we solved before, but it's just something that we just need to understand and then go through the problem. Now, a system shown below is taken from state 1 to A to 2, full stop. During this process, 289 kilojoule of heat flows into the system, which in turn does this work, does 110 kilojoule of work, which is 110 kilojoule of work. Heat flows into the system, that means it's heat accepted, and then which in turn does this work, that means the system responded by doing a work of 110 kilojoule. That means this is work done by the system. If you see it now, it said which in turn, which is the system now, in turn to reciprocate to the fluid or to the flow, heat flow that enters the system. This is what the system does. So it does a work. Now, how much heat flows into the system if part followed is 1 to B 2 to 2, 1 to B to 2 with this of work done. And then if the system is returned to state 1 by 2C1, okay, and 80 kilojoule of work is done on the system, determine the heat transfer between the system and the surrounding when the work done A is given as this on process A, that of process B is given as this, and that of process C is given as shown. Okay, so it's very, very simple, as you can see. Now, all right, so all we just need to do now is to first of all start taking the processes one by one. You see, why we are taking these processes is that if we decide to list all these parameters once, you will not understand it. Okay, so that's why you pick it process by process. And more also, the diagram that we are given now really does not represent what we have here, because we cannot see where they position A, where they call B, where they call C, and I don't want us to start guessing or manipulating our way around. But with this statement all, we don't even need this diagram to solve. Are you there? With these processes that we have here, we don't need the diagram to solve at all. So let's dive into solving this problem. So the first part now is to take part this, all right, is to take this first part on part process 1. For process 1 to A to 2, this is the first process. So under this process, we just need to list the parameters. So we're given heat accepted, which is Q as 280. Kilojoule. And equally, we will have work done. WA as. Alright, now for the work done on this system is 100 work. Are we there? The work done is 100 kilojoule of work. As you can see it here at the extreme end of the question, you have WA is equals to 100 kilojoule. So when we move down here, we have 100 kilojoule. Are you there? But as you can see, this heat was accepted and this work was done by the system. So now the first thing we are asked to obtain in this process, how much heat flows into the system, we need to first of all obtain the internal energies between these 2 points. What makes this particular question different from the first one we solved, the recent one we just solved before this particular one, is that in that case we were given the internal energy at the first point and we are asked to find the internal energy at the second point, right? But in this case now, we are not given any internal energy at any point, so we are to find the change in internal energy. All right, so to find the change in internal energy, all we just have to do now is change in internal energy. That this is unknown. So this is what we are going to find here in the first process. So all we just need to do is to recall the equation for the first law of engineering thermodynamics, and then if we say recall, Q minus W is equal to change in internal energy. Hope you can see this. And then because of this process, this is process 1 to 2, we can just call this Q1 to 2 minus W1 to 2 is equals to change in energy. Now to make this clear to us, change in energy here now becomes U2 minus U1, because U1 is taken to be the initial point, as you can see now, from 1 to 2. Okay, so what we just need to do now is to find the internal energy. Knowing fully well that we are obtaining the internal energy, we can just make it the sort of formula. So change in U is equal to Q1 to 2 minus W1 to 2. All we just need to do is to put in their value. Remember, the work done is 100 and then the internal energy, the heat accepted, is 280. So we put in the values. 280 minus 100, and then this will give us 180 kilojoule. This is the answer to this. So we have been able to get all the parameters that we need in process 1. So we now move to process 2. But one of the things you need to understand that as far as these processes are concerned, the internal energy remains the same. The only thing that changes is the sign. Maybe when you have a reverse, every other thing remains the same. Every other thing remains the same. Now, when you check the question, you will find out that here, let me change the color. You'll find out that at this point, we are asked to determine the heat flow or heat transfer between the system and the surrounding, and whereby the work done is given for each process. Work done for WA, WB, and WC. And then we have gotten the internal energy. So the only thing we are going to be finding out in the other processes that we have is Q, which is heat transfer or heat rejected. Now we move to the next process. I hope you are following and then you are catching up with what we are doing here. For process 1 to B to 2. Process 1 to B to 2. Process 1 to B to 2. Now all we need to do again is this. In this process, what are the parameters given? As you can see from here, we are given that in this process of B to this, that the work done. Okay, now we have stated these processes. All right, so we have process 1 to B to 2. So in this process, again, we were given work done. We now know our internal energy, right? Work done between 1 to 2 again on part B is given as, now if we scroll up, we will find out that the value is given as 48 kilojoule, right? So we just put in the value here, 48 kilojoule. This is the work done. And then don't forget that the change in internal energy is already known as 180 kilojoule. Why are we leaving this as 180? The process is still from 1 to 2. It shows that the change in internal energy here is still U2 minus U1, as long as U1 is the starting point. Are you there? 1 is the starting point. So it still remains as the initial value we have. So this is not changing to opposite sign. Then we are looking for what? Work, the heat. Are you there? Heat transferred. Okay, you can put it, actually this is heat transfer. Okay, so this is the heat transfer and this is unknown. So the same thing we are quickly going to do. All we just need to do is to recall that Q minus W is equal to change in internal energy. And then for this process again, 1 to 2 under B is equals to W1 to 2 and then is equals to change in internal energy. And this work done here is already given, right? So we can call this as QC, QB, right? Another way we can put this, then minus WB is equal to, then in this case we have change in internal energy. What are we looking for? In this case now, what is missing here is QB. So we just find QB by making it a sort of formula. We have QB is equal to WB plus change in internal energy. As we take the work done to the right hand side, it automatically becomes plus. So now what is our work done? Again, the work done in this process is 48. So we just have 48 plus the internal energy is 180. It's as simple as that. So 48 plus 180 will give us 228 kilojoule. Don't forget that this is the unit. And then this is positive, right? So because this is plus now, thus the energy that flows into the system from the surrounding is accepted. As you can see, because the value is positive, you can just say thus 228 kilojoule of energy flows into the system from the surrounding. So what is this kind of heat called? What type of heat is this? It becomes heat absorbed or heat accepted. Call it heat absorbed, heat added, or heat accepted, and then that value is plus 228 kilojoule. It's as simple as this. Very, very simple. Heat accepted. Heat accepted. But meanwhile, you don't actually need to add this plus here. Just remove the plus. As long as you said heat accepted, it covers up the sign. I hope you are getting values already. Now, what we are left with is process, the last process. All right, so it now said that if the system is returned, watch this sentence here. Return means reverse back. So when it is reverse back now, even with the equation or the part, you will be able to understand what is flowing here, what is happening here. So you'll be able to understand what is happening here. Look at it. If the system is returned to state 1, that means from 2 back to 1. Reverse process. So because this is reverse, something will happen to the internal energy. The internal energy have to change to its opposite sign. It will change to its opposite sign. In other words, if the internal energy that we have before is positive, the one we are going to use in this reverse condition will be negative. And if initially the internal energy or the change in internal energy is initially negative, now in this case now it will become positive. I hope you are gaining the principles one at a time, one after the other. So what we need to do now is to take this process for process 2 to C, then back to 1. So let's put that one here. For process 2 to C to 1. So this is reverse. What is the work done here, guys? Work done here, which is 2 back to 1, is given as minus. You can check it out here. All right, so let's move up so you can check it out. I think that's the last value here. See it here. And then if you read the question very well, it said if the system is returned to state 1 by this part and 80 kilojoule of work is done on the system. So even without extracting these parameters for us, as long as this work is done on the system, it should be taken as negative. Is that clear? Very clear. Anytime work is done on the system, that value must be taken or used as negative. I hope this is clear. So we just move down here and then we are good to go. So we have this as negative 80 80 kilojoule. Then we are looking for heat between this and this is unknown. So change in internal energy here from 2 to 1, for instance, will now be what? Minus change in internal energy from 1 to 2. Remember that the one we are calculating before is from 1 to 2, but the one we are looking for now is from 2 to 1. So automatically our change in internal energy here becomes minus. Now what value do we have before as our internal energy? You can check it here. Change in internal energy, as you can see here, is 80 kilojoule, right? So we can now take this as minus 80 kilojoule. I hope you understand why this value is changing to negative, minus 180 kilojoule. So this is now the internal energy. All we need to do is to recall that Q minus W is equal to change in internal energy, and then Q from 2 to 1 minus W from 2 to 1 is equals to change in internal energy, which is supposed to be U1 minus U2. You see it, huh? This is why it's changing to negative. And then by the time we decide to now put this in terms of the particular part, we can call this now as QC minus WC is equal to change in internal energy. So since we are looking for QC, we just make QC the sort of formula we have, WC plus change in internal energy. And we know that the work done in this process, as you can see, is negative 80. Can you see it? Negative 80. So we just put the value there because it was work done on the system. So I have minus 80 plus, and the value for this other guy is minus 180, as you can see. So this is minus 80 minus 180. And minus 80 minus 180 will give us minus 260 kilojoule. So as we have this now, we have been able to obtain the heat flows between the system and the surrounding for part C. Now the question is, what type of heat is this? Heat accepted or heat rejected? This is actually heat rejected. Why? Because the value is negative. It's as simple as this. So when you have a negative value, it shows that it is heat rejected. Therefore, or thus 260 kilojoule of energy flows out of the system to the surrounding. Are you there? To the surrounding. So what happens to this kind of heat that flows out from a system to the surrounding? Heat rejected, right? Yes, it's actually heat rejected. Heat rejected. You can call it heat rejected. And that value becomes 260 kilojoule. Like I said, you don't need to put the negative sign here once you put this condition here. All right, you can call it heat rejected, you can call it heat evolved, you can call it heat subtracted or heat removed. Hope this is clear. So these are the energies that flows in and out of the system. Are you there? In and out of the system. So we have been able to exhaust this particular question to its minimal level. So guys, I believe you have been able to also get massive value from this particular content. So guys, don't forget to leave a comment below if you have actually gained a lot of values watching this content. And then if you are yet to subscribe to this channel, do consider subscribing to this channel so you can motivate us to do more content amazing like this. And then don't forget to give us a thumbs up, don't forget to share, and then don't forget to recommend this channel as you've always done. We love you guys. Thank you for watching. I will see you in the next video where I will be teaching you again how to solve series of problems on engineering thermodynamics. We love you guys. Thank you. See you guys in the next video.